let's go ahead and get started. So today was supposed to be our MP2 demo day, and I think it's probably for the best that we push that a couple of days to Thursday. I won't push that any longer. I'm pretty sure, just based on what I was seeing, and I really only kind of see it sort of secondhand, that things are going okay. Just groups generally just need a little bit more time. What I had mentioned earlier in the semester in terms of how to kind of not survive, but how to really thrive in terms of debugging the labs, I think that's like hyper relevant right now. For the next 48 hours, it's very relevant for you, which is, I guess I would say, use the phrase being very intentional about how you're debugging and testing from this point forward. Little things like just confirming via hardware IDs and driver IDs, confirming that when you do run a test, when you take the time to run a synthesis run and test things on the board, that you're actually running the code you think you should be running. And I saw some groups still kind of trying to manage that appropriately. That's part of it. I think that's always important to make sure you're not spending time thinking you're debugging a change that in fact hasn't actually been reflected in the final hardware or software that you're working with. I think it's really important you do that just to kind of manage the time you have to spend. And then also just being very intentional with regards to the tests that you're running. Every time you do a new bit file build, there's a time investment associated with that. You might as well have an approach in which you treat it almost like a scientific experiment. It's kind of an engineering testing experiment, which is, I've made this change. I would write that change down somewhere in a file. It is 9:30 a.m. on a Tuesday, and I've made this change. I've changed this line of this file, and I'm going to try this. And here's what I'm going to try. Here is what I previously saw. Here is what I'm hoping to see. So that when you come back to it an hour later, you remember actually what the idea of that experiment was meant to be. I would also then, recognize that, well, I am changing my hardware. I might as well add more debugging hooks every time I'm otherwise going to change my hardware. So confirm for the various places where data can be flowing through the system that you have a little bit more inspection to what's happening than triangle shows up or triangle doesn't show up. I think for the first week, maybe the first week and a half, that's probably still sufficient. You're really just kind of trying to understand simulation. You're just trying to confirm, hey, does the idea that kind of covered partially in class, mostly in lab, does it make sense? Does it work? Is it doing what we think it's doing? Okay, every team has now gotten to the point where they kind of, sort of, maybe partially have something working, but it's not what you want it to be. And now you got to figure out, okay, red triangle works, but when I turn it upside down, it doesn't work. Let's build a test that does exactly that. Let's look at what signals or other aspects of the system I can inspect when I do this next test to provide me additional insight other than just the binary result of work, pass, fail kind of result there. Do that, and do that for every test you want to run, and I'm guessing most teams probably just have a couple of lines of code that you have to fix. And the trick is finding those lines of code and not accidentally breaking other stuff that was already working in the process. But be deliberate when you do that. And what also can help, although I'd love to help people debug if it's not working for them, is my intention was that those Xilinx machines, those remotely accessible ones, were supposed to be appropriate for just deploying your bit files and testing your OpenGL code. The idea was, you don't want to be in the Cougar lab anymore. You want to try something very small. You maybe run it either on a VM or on your own laptop, on Vivado, and then you deploy it on that Xilinx whatever machine that's supposed to be working for you. So if it's still not working for your team, let me try to help you figure out what environmental variable or other library or something is messed up in your configuration, because that was supposed to kind of make life a little bit easier as well. My thought was always, okay, it's late, it's time to go to bed. I'm going to run one more test, and I'll run it on this deployment machine so I can just go to sleep and come back in the morning and see what the result was or was not at that point. But be intentional with what you're doing, and I think you're going to be okay for Thursday. My goal, the requirement of MP2, is that you do get those examples working. Certainly red triangle. Snowflake's actually a little tricky. I mentioned that in the one video, was it a week ago back on Thursday. Snowflake's a little tricky just because of the really tiny triangles, and so it is actually quite a few different types of triangles, even though it doesn't look like much when you visually inspect it. The triangle paint is a really good one to test as well, because that lets you determine for one individual triangle in isolation what characteristics of the triangle may or may not be causing problems. The other one then would be like the random triangles, whatever it's called. That's more of a stress test. Is all the handshaking between your individual subcomponents, both inside the rasterizer and downstream of the rasterizer, are those all working properly? And then finally, really the only one that kind of tests your primitive assembly and the whole thing taken together is that color wheel one. So that would be the rough order I would do those. Personally, it's nice if you get Snowflake working. I think you can probably test it via other mechanisms, but red triangle, I would say, manually modified red triangle is like the next few things you're testing. That triangle paint application to really just kind of confirm, okay, really skinny triangles work, upside down triangles work, all these other types of triangles all work. Then rand triangles, and then finally color wheel. And you really just want to kind of get them down one by one and see what's happening here. Finally, just the last point I have is you may find, on Wednesday, it'll be I think a slightly different Wednesday for you because now you're fully in debug mode on a Wednesday, and that's not normally been the case. It's been design, it's been reading the assignment, it's been small debugging, but now you have these 3 hours on Wednesday where it's full debug mode. You may be able to split up the team in a logical way to allow you to debug different things that are kind of orthogonal. If you know that, for example, something's still wrong with your frame buffer swapping because the triangle is just really, really flickery just for the red triangle, that's probably something that a team can resolve, or a part of your team can resolve just by looking at the driver, looking at render output, figuring out how do I do my swap buffers properly. But then you also know there's an upside down triangle that's not working. Take the other person or two other people on your team and work on that particular issue at orthogonal. Just try to keep track of all your code. Put a version number on everything you're working on. And when you're writing a test, you should write it down in your notebook or write it down in a file saying, okay, this is rasterizer version 47, driver version 95 or whatever it is, render output version 17, and that's the version that we're currently checking. Because you may find you need to go backwards, but if nothing else, you just want to know that, okay, each test now is taking you a good half hour or more, right? Each time you want to try something on the board, I'm going to run this test, I don't want to waste that half hour. You only have so many of them left. Any lab questions before we kind of continue on this lecture 4 topic? So Thursday will be our demo day, and I do expect teams to get it working. So I believe in you. I saw enough progress that people worked pretty hard on it over the weekend. Observing Discord doesn't really tell me entirely everything in terms of what's working and what's not working, but I get kind of a feel for what I'm seeing there. The design was meant to be kind of created as something of a template that you were modifying versus trying to recreate a rasterizer from base principles. If you find yourself tearing out a lot of the code that I provided, you could still very possibly get it working, but I think it's harder than otherwise working with the framework that is provided. Okay, switching gears, context to where we left off on Thursday with our second snow day or virtual day of the semester, and hopefully our last. We finished and we were talking about the rasterization algorithms, first for lines and how lines can basically be extended to triangles. And while it's a little hand-wavy and we didn't really get that much into the math of it, it's very similar to what we talked about in class with what you are implementing in the lab. You're effectively taking the line equations for the triangle, you're then calculating both in kind of the x dimension and the y dimension. What is the gradient, what is the change in these attributes as you go plus or minus 1 in the x or plus or minus 1 in the y, and you're kind of just stepping on a line-by-line basis. And you need basically two functions or two pieces of hardware working in parallel. One is the function or a piece of hardware that determines whether a potential pixel is inside the triangle or not. So we always have to determine that. Given an XY location, am I in the triangle or am I out of the triangle? We call that triangle test. And then we have a separate module or separate function that determines, okay, if it happens to be inside it, what should those attributes be for that potential pixel? In our hardware, and logically it makes sense, we can generally do those two things in parallel because we're stepping from x and we're scanning down a line, we're incrementing x by 1 as we go. Mathematically, it's easier to do that and just calculate the change, and I think back to the Bressenham's algorithm, to calculate the change in what our attribute should be going from x to x plus 1 versus to take an arbitrary x, y and calculate what those attributes should be. So that's what we do. We go step line by, or element by element in a given line, and then line by line, We, in parallel, calculate what should my attributes be. It's all the C5s and C6s and all the C values in your rasterizer hardware. And we also, in parallel, determine, is it valid or not? Should we be actually outputting this fragment, or should we just move on to the next fragment in our potential triangle? So looking back in the slides, certainly don't tell you how to do MP2 hardware. There's enough disconnect there that I think you can't look at those slides and say, oh, I understand the bug I have in my hardware. But conceptually, it's very much doing the same exact thing. So the algorithm is effectively the same. So now when we kind of look back at our logical view of the pipeline here, and we start talking about how can we sort of reduce the total amount of work to go from vertices to fragments, now it's not quite as connected to what you're doing in the lab. So we're going to talk about some important things. The three terms you're going to hear are clipping, culling, and then hidden surface removal that we'll be covering. We'll try to get to all of it today, otherwise after demo day we'll get to the rest of it. And the main disconnect here is that while for rasterization you're basically implementing all of that in the lab and you're almost done with it, for clipping, culling, and hidden surface removal, I would argue they're equally important. We just don't have a lab that implements those. They're valid project ideas because they were doable as a lab. There's just only so many weeks in the semester for us to build it. So from a very high level motivation, the idea behind this topic is that, as we've seen, there's a decent amount of math, a decent amount of calculation required to go from vertices to fragments. And we haven't covered it all yet. We haven't really covered the vertex transformations and some of the other primitive operations. Are there mechanisms to reduce that total amount of work by looking at the fact that we may be specifying some geometry in a scene, but we may not actually need that geometry in our final display? Let me show you what I mean at a very high level here, at a very, very big picture here. In the big picture, we have a scene that has a set of these objects that are specified in a coordinate system we'll start to refer to at some point here in the near future as being in world coordinates. Think of this, if you want, for our labs as values in the range of -1 to 1, or any sort of range we can come up with for our x, y, potentially z values as well. We can specify all the geometry we want in a scene. But separately, what we also wind up specifying as part of our scene declaration is a window, a subset of that scene that we actually only want to be displayed at any given time. So we're specifying two kind of contradictory things, or there's a little bit of a contradiction here in that we potentially specify all this geometry we're potentially interested in, but then we're also specifying, well, here's what we actually want to view. It's a little bit different than a viewport, although it kind of looks like it. This is more so for the entire world of what we may be specifying in our geometry, in our triangles. Here's a subset of that entire world we actually want to correspond to what's going to go on our screen at the end of the day. So again, in terms of our motivation, how do we cut down on some of the work that we need to do for our rasterization? One of the early optimizations we can look at is recognizing that fact that while we just happen to specify perhaps a triangle here, we may not need to then rasterize that entire triangle because we can recognize early on, even pre-rasterization, that in fact not all of that triangle is actually going to display on the screen. This is the term clipping, and I use the terms kind of together, clipping and culling. Clipping, think of it as scissors. We're cutting out what we don't want in a particular scene, so we're cutting our triangles. That's fine. That's where the term comes from anyway. Culling, to cull the herd, to get rid of the triangle entirely. That would be if we recognize that a triangle doesn't belong at all. So they're two sides of the same kind of operation. They're very similar concepts. One is, do we cut our triangle to keep part of our triangle remaining? The other is, do we recognize there's a triangle over here, we don't need it at all. We just get rid of that triangle entirely. But this is the same concept. How do we minimize or try to limit the amount of work that we have to do down pipeline by recognizing at the point of specifying our geometry that we don't necessarily, depending on how we specify it, need it all? And we mentioned it, your hardware doesn't do any of this. And unless you decided as a project idea your hardware does not do any of this, you can play around with this and see the results. We have the red triangle, and it fills a good part of the screen, right? It's pretty big, right? It fills part of the screen. Make it twice as large and see what happens. There's no clipping, no culling going on. It's going to look weird. It's going to look wrong and bad in that sense because we're not doing so. Similar to how we did rasterization, let's just start with lines and then we'll work our way to triangles. Algorithmically, it's very similar what we're doing here. just easier to talk about lines first. So for this image, actually we talk about points first and then talk about lines very briefly. So for this example image below, let's think about which points and lines should be kept and which ones should be clipped. And this isn't meant to be a trick question or anything of the like. Things that are outside of the box, so that point, for example, P2, should be clipped, gone. We specify the geometry, we send those vertices down the pipeline, we fetch those vertices. At some point, generally pre-rasterization, we should be able to recognize, oh, P2 is specified outside that range of what? It's greater than Y max and it's greater than X max, right? Just get rid of it entirely, just drop it. So for points, I think it's relatively straightforward. For lines, it's not as straightforward, but we can kind of tell when we see it, right? Okay, P3, P4 are both outside that window. Consequently, a line that is rasterized between those two vertices would be outside the window. We should get rid of it entirely. That's technically would be called culling. We're getting rid of the geometry entirely. But now we have these other two examples. What is that? P7, P8, and P9, P10, where it's not quite as simple as saying the vertex is outside the range, so the primitive should be outside the range. If you look at that P7, P8 example here, both P7 and P8, if this was a GL points primitive type, would be culled, would be removed entirely. But because now the resulting line that would be rasterized would actually still at least in part be inside the range of viewable world space coordinates here, we would actually want to do that so-called partial clipping here. The correct result for specifying our geometry would be something like that, where you would see the component of the line that would actually fit within that window, and instead you'd be dropping the rest. And same for P9 and P10 that we have there. We keep the parts that are inside the window and we'd be clipping the parts that are outside. So for removing things that are entirely outside, I think, we can think about how we would do that. Look at the parameters, determine if it's entirely outside. We need some mechanism for lines as well as for triangles that allows us to do this. Given a triangle or a line that is larger than our viewing space, how do we clip it back down to our requested viewing space here? I think I mentioned this already, but for points, it's pretty straightforward. If we have GL points, meaning it's a vertex that is just a single point, doesn't correspond to anything else in terms of geometry in our scene here. If it happens to be outside the window, meaning the value of X is not within X min and X max, and the Y is not within Y min and Y max. So points P2, P4, P7, P8, P10, I don't know, PH is kind of hanging out there. I don't know what that's doing there, would all get clipped. So for points, I think it's pretty straightforward. So pre-rasterization, you'd look at those vertices as they would be fetched, and there'd be a separate stage in our pipeline that would determine, it's called sort of early culling, early clipping, that would determine, okay, it's outside my range I'm interested in, just get rid of it entirely, don't pass it on the rest of the way. Line clipping is definitely a little bit harder, as we saw kind of the three scenarios here. If both endpoints are inside the window, we know we're good for those two examples here. They're inside, so the whole thing's inside. It's also not easy necessarily, but I think we realize what the scenario must be. If we have one point of our line that's inside the window and one point that's outside, we know we must clip. That for that part that's outside, we're going to kind of just truncate it to the part of the box that we're specifying as our viewable world space here. Where it gets a little bit tricky and why algorithms were invented to do this efficiently is what do we do when both endpoints are outside the window? Just based on that description, there is no immediately obvious answer for what we do when that happens. We will have scenarios in which both points are outside the window, so we can get rid of it. We'll have then points where both are outside the window, but we actually should retain part of it. We need some effective, efficient clipping mechanism to allow us to say, both points are outside, what do we do? What do we determine for that particular case? The brute force kind of naive approach is for lines that have one or multiple endpoints outside the window. just do effectively a brute force intersection testing and calculation. And when I say intersection here, I literally mean like the intersection of those two lines. So we have this line here. This is the line that is partially outside the window. We have this line here, which we can think of as the lower part of our bounding box here. And determine this new point here, we would just perform that intersection of those two lines to determine that new XY value here. It's a little inefficient, arguably it's very inefficient, because we don't know for those cases where both points are outside the window, we don't actually know which endpoints, which lines they actually do that intersection for. Effectively, we have to intersect for all four of our window borders here for every line that has 2 points that are outside the window. And for the same reason we went through all that effort to avoid actually calculating y equals mx plus b for our line rasterization, all that effort in Bressenham's line rasterization algorithm kind of sort of goes to waste if instead we have to calculate lots of y equals mx plus b's here for doing our line intersections here. So similar to how we really want to put in the effort to kind of minimize multipliers and certainly our dividers for rasterization, we kind of have to do the same thing, or the original genesis of this algorithm was for the same motivation and reasoning here. This is the Cohen-Sutherland clipping algorithm, where we start off with just a simple labeling scheme, which you could think of as one pass over the data that's going to assign a 4-bit region code associated with each vertex as it is applied here. The actual ordering of the region code doesn't matter as long as it's consistent and we can keep track of it. For this example and illustration, it's above, below, right, then left. And if I get that wrong today, just feel free to correct me. Where we assign that 4-bit binary code, and we assign it based on for that point, is it above the box? Then we get a 1 in that most significant bit. If it's below the box, the point, then we assign a 1 for that next significant bit. Then we assign this next bit as a 1 if it's to the right, and finally that least significant bit at location 0 if that point is to the left of the box. So each region, if you think of the entire world being then divided up into those 9 regions, is going to get a unique code associated with it, because it's either entirely inside the window, then it's all zeros. It's above the window, in which case it's going to have a 1 in that digit. It's to the right, it's to the bottom, or to the left. And we get that unique code associated with each potential region of the 9 possible regions inside and outside our window here. And then we go and we just assign each endpoint with its corresponding code. And we can think of how we would do that in hardware, right? You take your vertices, you would have to have, as some configuration state variable, you would have to have encoded somewhere the values of xmin, xmax, ymin, and ymax, and you would just do some less than and greater than calculations, right? Think of it, if my point x value is less than xmin, then set, which one was left again? Then set this least significant bit to 1. Or alternately, if my vertices x value is greater than the value of wx max, then set this bit to 1. Same for top, same for bottom as well. So for every vertex coming in without any real kind of additional slowdown of the processing of these vertices, you can assign that 4-bit code to them. If it's inside the window, it would wind up with the code of all zeros. There is no possibility for some of these, right? There is no 111 code because they're mutually exclusive, right? The point for an individual vertex is either above the window, inside the window, or below the window. It can't be both above and below at the same time. So given this encoding, it's not quite all 16 permutations here, but there's 9 possibilities, and we can pretty quickly do that labeling of the appropriate region code for each of those points as they come in. Again, you may be similar to what we did with Bressenham. You may look at it and say, well, I mean, yeah, that's one way you could do it. Okay, it's very obvious maybe in retrospect, but conceptually, these region codes make the actual calculations required a little bit easier in terms of quickly determining what type of clipping scenario we have or not and whether we need to do anything. So now we have not just individual points coming through, now there's some early primitive assembly, and now we have pairs of points for our lines. And so for our pairs of points, the effective operation we do is basically just an AND operation. If we AND them together and both sets or both pairs of region codes are all zeros, that tells us both endpoints of our line are inside our window, carry on. No clipping required whatsoever. Before I have it on the next slide, how would I quickly determine if I can get rid of the line entirely using the region code?
You AND them and it's greater than 0?
If it's not 0, I guess, right? If you AND them and there's a region code of 1 in common between the 2 points, so you can look at 13 and 14, and this bit is high and this same exact bit is high in the other location. Consequently, they're both below the lower bounding box here, and we can do an AND gate and check and then count, not 0 or what, count ones and determine if we have that region code in common. We don't have to do anything further with that line either. We can entirely clip, discard, cull that line entirely. Now again, conceptually that's not a change at all, right? It's a way of labeling the data as the vertices come in, such that when it comes time to determine whether we need to rasterize these lines or whether we have to do some clipping first, this calculation becomes very straightforward. We're not worrying anymore about comparing X and Y values to X-min and Y-min, X-max, Y-max. We now have just this single 4-bit code. We have done the comparison once per vertex, but now given all these vertices, we've done all those comparisons, now we can very quickly determine, at least for now, these 2 scenarios. It's all zeros, good. Pass it on. It's got a 1 in common, like at the same location, good. It's bad. We don't need it anymore. We drop it at that point. So that stage of determining what to do becomes much more efficient than it was potentially before. We still have the tricky case, which is lines that can't be identified as being either completely inside or completely outside, and they may or may not cross the window interior, and here's how the algorithm effectively processes those lines. We first compare the endpoint that's outside the window to a boundary, and given the region code, we can determine pretty quickly which boundary to actually compare it to, and determine how much of that line can be discarded. From that new line, from the new point we wind up generating, we go through that same region code comparison again and determine we've clipped it to the boundary, the nearest boundary. Is the new line that results from that, is it inside the window or is it entirely outside the window? And we can determine whether it needs to be clipped or continued. And the region codes is what also then makes that easier as well. As opposed to kind of the naive approach, which would say we have these 2 points, we have to compare it to all the potential lines of all of our boundaries of our window. The region code tells us it's above the window. We have to compare and clip against the top side of the window, or it's to the left. We have to do a clipping against the left side of the window. We can relatively quickly, in terms of the number of steps required, determine, given that point that's outside the window, what would the clipped point be that is actually touching that particular boundary? What would the new region code be for that new point that we have generated? Should we keep the line or should we now discard the line at that point? Let's do this quick example with P9 and P10. So P9 is inside the boundary, we don't have to do anything with it. P10 is outside the boundary with the region code for below. From the 2 region codes, we know it doesn't cross the left or the right boundary. We don't care about that one at all. They're all zeros for left and right. But we can see that it is, the line is crossing the bottom boundary. So we would then have to calculate that intersection of P10 with that lower boundary. That would require us having some knowledge of the line equation for that line. We need to do that for rasterization anyway. We don't actually avoid that slope calculation, but we just want to minimize the amount of times we have to use that. So we calculate that intersection, right, of this line with this particular line to get this new point P10 prime, whatever you want to call it, which would have its own region code. It's on the window, so it would have a region code of all zeros. That new line, P9 to P10 prime, it's all zeros. It's completely inside the window, so now that new line is what gets generated. So you can think of this clipping module, if you want to place it in your pipeline, as taking primitive as input and outputting primitives as well, but potentially dropping some primitives along the way, passing some primitives completely unchanged through the pipeline, and others modifying it as it goes. This takes a line as input, outputs a line. It's just a different pair of vertices based on the clipping operation here. For P3 to P4, again, in this example, we can't just do the AND operation of the region codes to determine that we need to drop this line, but we do need to drop this line. In looking at the region codes, we can see that as we go from P3 to P4, there's a couple things we could check, but the first thing we can check is that rightmost code, which is for the left boundary, that goes from 0 to 1. So that would be, as it goes from 0 to 1, that would be the line that we would want to intersect it with. So it crosses the left boundary. We could then calculate the intersection of that line with the leftmost boundary. In doing so, we would get new point P4 prime. And unlike the naive approach where we would have to continue to check against all the other boundaries, we've calculated P4 prime. Its region code is also now, I want to make sure I get this right, is also now to the left of the line, and consequently we do the AND. It's not inside the window at all. We can drop the entire line at that point. So now the example where both points are outside the line, but actually there's quite a bit that would be inside. The order of this doesn't necessarily matter, but let's say we start with P7. Looking at the region code going from P7 to P8, we recognize that it again crosses the leftmost boundary. So we calculate the intersection of P7 from P7 to that leftmost boundary, X min there. We do the same thing from the P8 side because it crosses the rightmost boundary. So we calculate the intersection of that line with the rightmost boundary. That gets us new points P7 prime and P8 prime, all zeros for our region code. We would then pass that primitive down for our rasterizer to do the next step. Let's do one ourselves. I think we can hack it. Maybe, maybe not. I won't make you break into groups today for this. I know you're thinking triangles and rasterizing and trying to debug traversal in your heads. That's good, but we can still do this one as well. What would make this easy? Well, okay, we could do our region codes, right? P1, we'll call it on the left, P2 on the right here. P1 is below and to the left, so it's 0, 1, 0, 1. P2 is above and to the right, so it's 1, 0, 1, 0. First step, do we AND those two region codes together? 0, 1, 0, 1 and 1, 0, 1, 0, nothing in common, so we can't instantaneously kind of drop the line entirely, but it actually crosses all four borders here. So we could do the intersections with all four borders, or we could just pick luckily and just do two intersections to start with. So we can do the intersection with this border first, from this first point to intersect now with this first border. What's the equation of this line? Happy Tuesday morning. What's the equation for that line? Okay. The slope is 1. There you go. What do you do next? You plug in a point. What is the slope is 1, so we plug in 10. We get 14 equals 10 plus b, so b is 4. So y equals x plus 4 is that line, I think. You can plug in any point. We only have 2 to choose from, so you plug in any of those 2 points. So I'm not going to write it on the screen. Remember that y equals x plus 4, not coincidentally meant to be a relatively straightforward line to calculate. What is the equation for this line? The bottom border. It's y equals 2. Thank you. So one equation is y equals x plus 4. The other equation is y equals x plus 2. What would the intersection between those 2 points be? Those 2 lines be, excuse me. Right, 2 equals x plus 4, x equals negative 2. We'll just have to remember it. We would then generate a new point, negative 2, 2 here. We would also have to generate a point here. The equation here is x equals 4. So y equals 4 plus 4. This would be 4, comma 8. The end result would be, and we could have also compared against the other regions, but it wouldn't really change the end result here. Compare those 2 points that we've now generated. They're both on the box, they're both in the window, so they would both have a region code of all zeros. That would then be the end line that our clipping module would generate for us here. That's what lines. Life gets a little bit more complicated with triangles here, and this is kind of the reason we also don't do this in the lab. These examples are meant to be arbitrary. I've talked about how if we want to guarantee our geometry is convex and simple, we would generally be specifying triangles, but conceptually at a very high level, this is what polygon clipping would have to look like, right? So areas, not just the lines themselves, would have to be clipped to a window boundary, and we'd have to keep track and be very careful to keep track of what portions of the initial area would be retained and what portions of the initial area would be clipped. Another way to think about this, and I don't have a good visualization on this slide, the reason this is harder is because we have a triangle, right? Even our red triangle or our black triangle here on the board. Now the scenarios, again, for the single line case, the scenarios weren't so bad. Toss the line, keep the line, or give me a shorter line, right? Those are kind of the three outputs of our clipping module when it's clipping lines here. Now when we're clipping triangles, our scenarios get a little bit sketchier here in terms of what the output of this module would need to be. Of course, red triangle fits inside our window. Retain the triangle, no problem. Likewise, window number 2, triangle's completely outside of our window, no problem. Toss the triangle, we don't care about that particular triangle. What other scenarios can you see here that we'd have to do?
Some of the points are inside the window.
Some of the points are inside the window. So what happens when our window is this? Oh, it'll happen, obviously. I mean, you can do that with the red triangle right now. Just make it bigger. That'll effectively what happened. That one, okay. Maybe we have, depending on how we do our rasterization, maybe we say, we can't handle that case. So we just pass that triangle on and recognize that we're going to be generating fragments that we have to drop somewhere else along the line. So there's kind of, in modern hardware, there's sort of an early clipping stage that happens, and then there's a late, last-minute clipping stage that happens. Where it gets really kind of interesting and or tricky and or fun and or nasty is we had a triangle, we then have our window specified like this, and what do we have as the output? It's a trapezoid, right? It's, yeah, like more than one triangle is left. So now it changes fundamentally, not just, line or no line or shorter line. Now it's 3 points were our input in terms of our vertices. To make sure we're actually generating this trapezoid, somewhere along the line, someone's going to have to get clever and generate the fact that this is now going to have to be a triangle strip. I think with a triangle, it'll never get, no, it could get worse than that, right? We could have this as our triangle, and for all those intersection points, the nice thing about a triangle strip is it doesn't really complicate the rasterizer any, but now it's doing more work, right? Because now there's more actual triangles that are going to get generated by your primitive assembly module here. So conceptually, we can do something very similar. We can look at region codes, and we can kind of trace, like we trace the line, we can kind of trace the edges of our polygon or our triangle to determine, have we gone from inside the square or inside the rectangle to outside the rectangle, or outside the rectangle to inside the rectangle, or were we outside the rectangle the entirety? But the complexity here is now the end result is going to be input was 3 vertices composing a triangle, output is 1, 2, 3, 4, 5, 6, or however many vertices composing a triangle strip. The challenge is a little bit heavier here. This example is just a bit extreme in that it's showing these concave polygons that we're not expected to be able to rasterize anyway. But in general, this issue up here of keeping track of what portions of the area are clipped makes this a harder problem than the line clipping algorithm here. This is a very similar and related algorithm from the same group, the same people. This is the Sutherland-Hodgman clipping algorithm, where we're going to clip an area against an individual boundary at a time. So another way to think about this think of those as 4 different steps happening. I think sequentially, I don't think it would be done in parallel. So you'd think about not just a single clipping, but it would be 4 clipping operations that we'd be doing here. So we would consider each vertex against a particular boundary at a time. Any vertices that are inside that boundary, in this case, if we're flipping to the left, we keep all the vertices that are to the right of that leftmost boundary. We keep those, and anything that is going to be outside that boundary are going to be clipped, and we're going to proceed from vertex to vertex. We're basically going to walk through our array of vertices. Again, we're not going to do it for a star formation in practice, but we would do the same thing for a triangle. So conceptually, it's very similar. We're going to walk through our vertices, and we're going to determine when we go from inside the clipping region to then outside the clipping region, likewise from outside the clipping region to inside the clipping region, then we're going to treat that like our line case again. So we can think of it as, it's a primitive, it's a triangle, it's a star, whatever shape we have. We can think of it now for this stage as being composed of its constituent lines making up its edges, and we're going to do an edge walking of that shape to determine, did we go from inside to outside or outside to inside? It just gets a little bit trickier now that we're looking at areas and not just lines. We're going to do a single step of doing it for left, then for, or the order doesn't necessarily matter, then for right, then for top, and then for bottom. And the end result, as we show even for the triangle here, could be a piece of geometry with a certain complexity coming in and a much more complex, much more vertices coming back out as our end result here. This example is a trapezoid, which is a little bit better here for Sutherland-Hodgman visualization. So as we're clipping on our left-hand side here, we have some start point and our current point being processed. So let's assume it's that upper right vertex that we're starting with, and then we're going to move from that point to the next point. We move from S to P. Look at the region codes. Both points are inside our viewing region, inside our clipping area here. We keep them both. Then we proceed in our clockwise manner. From previous point is now the current point to our next point, P. So that's that lower right point to the lower left point here. We look at the region code for those two endpoints, and we see one of them is inside, one of them is outside. We have to do that Sutherland line clipping approach where we then calculate, given the equation for that line and given the equation for that boundary, what that new point must be. We actually then keep that point, and that becomes part of our output geometry here. But we actually still continue here. So we kept point, I'll kind of just show it on here. We keep this point S, we keep this point down here S, we then keep this point I, and that's our third point of our geometry. We then still continue, and then we go from this point now to this point. Look at our region codes, both are to the left of our viewing window here. We drop both of them, we don't include any of them in our output geometry. Finally, we go from this last point back to our original starting point, and we do that same operation. You recognize that we're going from outside the window to inside the window. We perform that intersection with the leftmost edge here. We have an additional point that we've kept here. So the end result here isn't too scary. We start with 4 points in a trapezoid-like quadrilateral. We wind up with 4 points in a slightly different looking trapezoid. Conceptually, that's how we would do this. The tricky part then just becomes, for our triangle, we'll stick with this example here. We start with this point 0, we go to point 1, we'll call this point 2. We go from 0 to 1, they're both inside, it's fine, we keep them both. We go from 1 to 2, we recognize that we go from inside the region to outside the region, we then have to keep that point. We then go from 2 back down to 0, we calculate the intersection point. Our input was 3 vertices, our output was 4 vertices. The same exact approach goes here. I won't label them all, but it's the same process. We start, we have to calculate our intersections. We store our intersection points as we go from outside the boundary back to inside the boundary. And the end result may be from 3 vertices as input to potentially more, potentially 0 as output, of course, if it's entirely outside the window. Potentially the same 3 vertices as output if it's entirely within the window, or some additional number of vertices, specifying, in fact, a different piece of geometry than what otherwise we originally intended for that primitive. How are we doing with this? Should we keep going? There's a couple more important things we need to get to, but if we don't get to it till Thursday, that's fine as well. Okay. there's a 3D analogy for this. I think for now we haven't covered viewing properly at all. I think a high level of visualization of what has to happen in 3 dimensions is probably sufficient for our purposes. We keep thinking of this as being, you know, the 2-dimensional kind of viewing transformation of what's happened here. We're worrying about kind of the screen and what's going to be displayed or not on the screen. But when we originally specify our geometry, it's got that 3rd dimension as well. As part of that specification of our geometry, we are also going to be learning about how we're going to specify basically a viewing transformation. One physical analogy we use for those viewing transformations, and we really don't get too much into the math of it all, you know, there is a lot of it at that point, but one physical analogy for the viewing transformation is we're setting up like this virtual camera, which is what do we want to be able to see in my scene? What do I not want to be able to ultimately see in my scene? One way we set up our viewing transformation creates effectively, usually the truncated pyramid here. There's other viewing transformations that would set up some sort of cube or just 3-dimensional rectangular prism. Ultimately, however we set up that viewing transformation, we're going to have the same issue, which is some stuff that we specified we want to actually see. Other stuff we specified we actually don't want to see. Yet again, other stuff that we specified we want to see part of it, but not the entirety of it. So clipping has to actually also happen in that 3D and that 3rd dimension as well. But as we'll start to talk about, there's a slightly different issue that comes up when we do these viewing transformations also. Not just the fact that we have to discard things. I think a hand-wavy argument can be made, it's not so different than this, discarding things in the 3rd dimension. We just have to compare against a 3D window. It becomes very hard to draw and kind of show, but it's just another, instead of X-min and X-max and Y-min and Y-max, we also have Z-min and Z-max, and we're doing the same kind of operations there. Instead of a 4-bit Sutherland code, there's a 6-bit one. It's a similar set of operations. But when now we have this thought of like there's the 3rd dimension here of objects that are specifying at varying depths, distance from the camera, there's a couple things that we have to keep in track of that are a little bit different now. The first one is we have to recognize that as our potential geometry is also 3-dimensional here, some objects are going to be facing the camera, other things are going to be turned around and not facing the camera. That's one thing we have to watch out for. What's the actual direction that our primitives are actually facing? Other thing we have to watch out for is we have these objects and it's a 3-dimensional view of what's happening in our scene. Ultimately though, it's still going back to a 2-dimensional display at the end of the day, for at least traditional rendering approaches. It's going to a 2-dimensional screen, so we have 3 dimensions of our objects. And how do we determine, for example, just at a very high level, that we have this green cone, if you can see it here, and we have this little blue, purplish kind of cube behind it. And while we specify both of those in these 3 dimensions, we actually keep them both because we're not clipping any of those away. But ultimately, the green cone being closer to the camera should be blocking partially or entirely that entire object of that 3-dimensional cube here. So it's related to clipping, and again, we can still do 3-dimensional clipping, but then there's 2 other things we have to kind of also take into account here. Again, one is we do have to actually determine whether we're not actually facing the camera or not. Are we behind, are we facing the opposite direction, are we facing towards the camera? But then we also have to determine for our depth dimension here, for our Z dimension here, what things should we actually keep and what things should we drop? It's related to, but it's not the same concept as clipping here. One would be referred to as back face visibility detection. The other one is just called hidden surface elimination. And there's all sorts of different algorithms for doing both. The most important ones are referred to as these image space methods. It turns out that determining whether or not a polygon is facing one direction or the opposite direction, we can take the normal of it. That's not too bad mathematically. Determining to what extent one object is in front of another object is a much harder problem to solve. We'll look very briefly at some object level algorithms for doing that very briefly. The most common ways instead kind of completely punt on the issue at the time of object specification and instead say, let's just keep track of that z dimension as long as possible. Let's keep track of it. Only when it comes time to actually write things to our frame buffer do we then compare and determine we have two potential depth values. One fragment is further away than this other fragment that's at the same xy location. Let's keep the one that's closer to us. That's so-called image space approaches, and they're much more common than the object space approaches. You can also use a combination of the both. If you've heard the term z-buffer, other places just refer to that as render output operations, render output buffer operations here. That's what I'm referring to with that hidden surface elimination approach. And that's what I was mentioning here. So there's object space methods and image space methods. The object space methods determine on an object by object basis. You can think of it as like maybe like a sorting type approach for our primitives. The approach we'll learn very briefly is the so-called painter's method, where I know I'm going to be painting a lot of things in my scene. I can determine what order I do the painting, and that kind of solves the problem for me. I paint the background first, then I paint the faraway layer next, then I paint the successively closer and closer objects as I go. That's dependent on the person specifying the geometry to determine what order things should be in here. The companion and complementary approaches, the depth buffer or image space methods, where on a fragment by fragment basis, we determine should this fragment be actually drawn to the screen or not. Let's check how far away it was from the camera before we do so. Let me skip back face detection. Yeah, we have to determine for our cubes whether something is facing the camera or not. We'll get there when we talk about viewing and transformations. That's an appropriate point to talk about that as well. So one depth sorting method is the so-called painter's method, where we basically are sorting our objects in order of decreasing depth, and we specify those objects in that particular order. Again, another way to think about that is, give me the object that is furthest away, and I'll draw that first. Then on top of that, I'll draw the next object that's slightly closer, and then the next object that's slightly closer, and then the next object that's slightly closer. That kind of sort of works. It doesn't entirely work because we have all sorts of three-dimensional objects that are going to be, partially overlapping or self-intersecting objects and things like that. So if, though, we had a particular scene in which there was no particular depth overlap, then this kind of sorting approach, whether done at object specification or via some clever, rasterization time sorting of objects, would work entirely for us. Again, this view is meant to show kind of the two dimensions where we care just about either the x or the y here. And then the z range, that is the so-called depth parameter. We've been setting it to 0 for all of our input geometry. We're not doing any viewing transformations yet. You could set your z to anything and it would probably be okay within -1 to 1. But ultimately, at some point, we're going to be setting that depth information. And one way to conceptualize what's happening with that depth information is it's how far away should this object be? Think of it as the person viewing the scene or a camera taking a picture of the scene that you're setting up. But either way, that z information is encoding how far away should this object be. Larger z value than being further away than smaller z value. There's all sorts of state information OpenGL lets you set about that. You can flip what's far and what's near. You can determine what to do with negative. You can set the precision of it. You can do all sorts of things with it. But conceptually, it's something like this that we can then use to apply an object space ordering mechanism, by which we would say we have this object that's at a particular z-min and z-max, because it wouldn't just be a single value of z for an object. A vertex would have a single z value, but a triangle would have a gradient of those z values like it does for any other attribute. Just like a vertex has a single RGB value associated with it, but the triangle has a gradient of color depending on how it's changed as it goes. It's hard to draw it as part of the issue, right? But we have our triangle, we have the attributes specified for it. X and Y are also, those are positional attributes. As we specify our geometry, we'd also be specifying a z attribute. And that z attribute would be one way of saying how far away is this vertex or this triangle from the scene that we are trying to view here. Depth. How far away is it from us? And they wouldn't have to be the same. I mean, we draw this as kind of a flat triangle, so we think of it, as being the same. But this point in the triangle, this vertex could be very close to us. This one could be very far away. This one could be somewhere, in between. We could take what's still this, basic two-dimensional shape and then just kind of rotate it in that third dimension to give us all sorts of different types of geometry, right? So for the depth the painter sort algorithm here, we can look at our objects, and this is quite a simplification of what would ultimately be happening. We can say triangle 1 would be S, and triangle 1 across its vertices has a minimum depth and a maximum depth. We don't have to do rasterization to determine that. Just like for your triangles, you don't have to do rasterization yet to determine what's the largest red value and what's the smallest red value for your triangle is going to be. We haven't calculated what all the values are going to be, but it's going to be some combination of the three, right? Or some extremes of the three. It's not going to be more red than any of the three vertices here, nor is it going to be any less red than the least red of these three vertices here. The same goes for depth. So you could calculate relatively quickly Z min, Z max. What's the closest point in this primitive going to be to the camera? What's the farthest point in this primitive going to be in the camera? And you can do that for all of your triangles, for all of your objects in a scene. And for those that don't overlap at all, we can then render our scene by just then drawing them in furthest away to closest to us order. Draw all the far triangles, then draw all the closest triangles. But I think you can come up with all sorts of scenarios in which that doesn't really entirely work in practice. This is one such visualization of a scenario. There's other scenarios we could show as well. This would be two objects, although we're not showing y dimension here, so we can't say for certain. But these are two objects, one of which is going to kind of intersect the other. The one object has a certain depth, z min and z max range. The next object has its own z max and z min range, and there's an overlap between the two. That doesn't guarantee the two objects will intersect because we're missing some information here. Without the y and actually showing it, we can actually look at it and maybe we determine that this scenario is still okay to draw in reverse depth order here. But we have to do that extra step algorithmically to determine it looks like these two objects may be intersecting because we have this range of z in which they intersect, as well as in this case, for the x dimension, there doesn't look to be any potential overlap here. We have to then check it at that point and say, do those two triangles intersect or not, and draw from back to front if they do not intersect. We can do a bounding box calculation. Does the bounding box of one intersect with the other? Can we also guarantee that from the viewing transformation that's happening, do they wind up not intersecting when viewed from that perspective and that angle? But in general, this approach is less common because for scenes that we generally would want to be interested in rendering, we would have our objects actually intersecting with each other. So we can't say, unlike a painter, right? That's why it's called the painter's algorithm, right? We want to draw the background, and then we draw the happy little trees, and then the clouds, and the birds, and things like that in front. We draw things in order here. Sometimes we go back to the background and add a little bit more detail, as long as it's not overlapping something we've already drawn at that location here. That works for a painter's algorithm. That works when you're actually painting something on a canvas. But that works because your brain is calculating all that perspective either as you go or in advance. You have a mental image of what you want the scene to look like. You yourself are determining how I'm going to draw these objects, how I'm going to draw what would otherwise be geometry that would be intersecting in such a way that it looks visually close to what a three-dimensional object would look like when we're dealing with our graphics pipeline and when we're just specifying these triangles as we go. It's much less likely we can guarantee that we can do that kind of sorting approach. The depth buffer approach is pretty important. Let's cover it on Thursday after our demo day. So let's leave things here for right now. I want everyone to kind of just move over to the lab after class, or at least meet and discuss and have plans. I'm positive you can all get it done for Thursday's demo day. You just gotta be intentional with what you're doing. You just gotta be organized. You may need to have someone who's just one of their primary contributions is keeping good track of where the state of everything is at, and always be asking, why questions as you're debugging things. Think of it like a science experiment. You're in the chemistry lab. I'm just going to mix these two chemicals and see what happens. I mean, that's fun, and you can do that. But when you really want to get a particular reaction to work, you have to really be very meticulous with what test am I running, what specific result, and here I mean like either ILA results or something specific on the screen. What am I expecting to see? What did I actually observe? What hypothesis can I then, come up with to determine why would it be doing that when instead I was expecting it to do this? That can be hard when thinking about digital hardware, that kind of hypothesis generation. But it is better than just staring at the code and saying, let's try 4 for this number and see what happens. I understand how you get into that state, and I do think there's enough like low-hanging fruit that just staring at the code you may fix a lot of bugs just looking at what you already wrote. I do get that. But once you think you've done all that and now it's still not working, start some hypothesis generation and testing. Be very intentional with the tests that you do run. Just do the math. If it's going to take 30 minutes per test to do a full synthesis run and test and kind of collect results, that's a good estimate. How many tests do you have between now and Thursday? 10, 15, 20, it's not that many, right? At most, right? So each one is kind of precious, so be intentional with it. I think you'll see that you'll make more progress. Even if not every test is going to lead to a bug that you fixed, you'll hopefully at least learn something with each test you have along the way. Let's leave things here for today then. I expect you all just to go sprinting to the lab and making rapid progress. Otherwise, I'll see you on Wednesday. I'll stop by on Wednesday, and then otherwise I'll see you guys on Thursday for our demo day. Thanks.